Welcome. Today we're breaking down some really fascinating source material on what looks like, well, a pretty definitive turning point for AI development tools. We're talking about the arrival of GPT 5.1 Codex Max.
Right.
Look, if you've been following this space, you know the drill. We've been promised the AI that will, end late-night debugging for years.
And it almost never works out.
It almost never works. The models fall apart the minute you point them at a real, messy legacy code base. They just lose context. But the material we've been analyzing suggests that this Codex Max, it feels different, that's the quote, because it was trained to survive those long, messy projects.
And that's the whole shift, right?
Yeah.
It's not about writing perfect snippets anymore. It's about sustained autonomy.
So it's not just a clever autocomplete in my editor.
Not at all. This thing operates as a persistent, autonomous agent. It lives in a sandbox environment.
Okay.
And it can maintain a coherent train of thought across hours of work. It navigates files, it edits code, runs test suites, reads the errors.
And it learns from its own mistakes.
It learns and recovers from its own mistakes. You should really think of it less like a tool and more like a junior engineer who just never gets tired. And it remembers everything it did for the last 24 hours.
That sets the stage perfectly. So let's really get into it. We need to unpack the core innovation here, this compaction engine, and then look at the actual performance benchmarks. What can this thing do?
Let's do it.
All right, so let's start with the architecture. What exactly is GPT 5.1 Codex Max? How does it get around those memory limitations that have just plagued every model before it?
It's all about its specialization. So, yes, it's part of the OpenAI Codex family, but it's really an agentic specialist. It's not a general-purpose chat system.
Agentic specialist. What does that mean in practice?
It means it's built to execute actions on its own, to run code, coordinate with tools like compilers or build systems, and navigate huge code bases across what the sources call long horizons.
Long horizons. Ground that for us. Are we talking about a task that takes a few hours or a few days?
We're talking about tasks that would normally require a human developer to, stop, commit their work, and then pick it up the next day, rereading everything to remember the plan. Hours, maybe even a full day of continuous work.
Okay.
And the reason it can handle those long horizons is its core trick, compaction.
Right.
Previous models had that hard limit, the context window. You start a big refactor, and by the time you're modifying the third microservice, it's forgotten the constraints from step one.
And it just stalls out. Or worse, it starts hallucinating a solution that doesn't even match the original problem.
Exactly. Falls off the token cliff. Compaction changes that. Instead of one massive context window, the system can compress and stitch multiple windows into one long task.
The analogy they used was zipping the important parts of its memory. Right.
That's the one.
Yeah.
It zips up the goal, the test failures, the high-level plan, so it can carry the essence of the entire session without losing the plot.
Okay, let's dig into that mechanism, because that is fascinating. How does it decide what gets zipped? Is it just summarizing text or something more complex going on?
It's more complex. It's abstracting the plan and the critical dependencies. The agent is trained to spot structural markers like function signatures, class hierarchies, and especially the failed test outputs.
So it prioritizes the map over the terrain it just crossed.
That's a great way to put it. It holds on to the high-level map.
And that capability has to make a huge practical difference for any team running a modern infrastructure. I'm thinking monorepos, microservices.
Absolutely. Because the compaction doesn't just help it remember things, it lets it trace bugs across those boundaries.
So if you have 5 services that all touch, say, the user profile.
The agent can modify logging in service A, then update a database schema in service C, and roll out a feature flag in service E, all as part of one coherent 24-hour mission. It navigates a technical landscape that used to require multiple humans.
Okay, so if it can handle that kind of complexity, let's talk processing power. The sources mention it's not a single pipeline. There are different reasoning tiers, and I saw a visual of an xHigh toggle.
Yes, the reasoning tiers are key. They let developers make a trade-off between latency and reliability, depending on the job.
Okay.
The first tier is medium reasoning. That's your daily driver. Optimized for speed. It's for bulk tasks, scaffolding a feature flag, wiring a standard API endpoint, cleaning up a helper module.
Quick and dirty.
Fast and reliable for conventional tasks, yeah. It's your low latency default.
And then there's the big gun, xHigh reasoning.
Exactly. That's the deep focus mode.
Yeah.
You flip that toggle when you have a problem that would normally just consume a senior engineer's whole afternoon.
And it just slows down.
It deliberately slows down. It takes on higher latency. But in return, the model gets significantly more internal compute and a longer, more thorough chain of thought.
If everyone's hitting that xHigh toggle for their hard tasks, does the whole system grind to a halt? What did the sources say about resource scheduling?
That's a great question. The sources imply that because it's so compute-heavy, xHigh tasks are scheduled and rate-limited more aggressively.
So it's a design choice.
Right. The system basically encourages you to save that expensive, high-reliability compute for the problems where failure would be a disaster.
So when does a developer make that trade? When do you say, oh, okay, I'll pay the latency cost for this?
You do it when reliability is everything. Think about the tasks that cause real pain.
Like what?
Untangling a legacy data pipeline, refactoring a fragile domain layer that nobody's touched in 5 years, or chasing down a subtle race condition that only shows up under heavy load.
Oh, yeah.
For those brittle, painful tasks, trading a few extra minutes of AI latency for hours of human misery is always a one deal.
And this is what enables that whole 24-hour coder workflow. It's not about quick fixes anymore. It's about treating the AI like an autonomous agent on a mission.
That workflow is the real transformation here. It's iterative. You describe the goal in natural language, say upgrade the Ophuth library across all services. The agent plans the steps.
And then it just goes.
It edits the files, runs the full test suite, reads the failures, updates its plan based on those errors, and tries again. And because of compaction, it can do that loop for 24 hours straight without ever forgetting what it was trying to do.
It sounds amazing, but does this mean we're just trading the agony of a late-night debugging session for the new agony of trying to debug the AI's complex plan?
Hey, that's where the developer's role shifts.
Yeah.
You're not the fixer anymore. You're the auditor.
Yeah.
The mission setter. You're not debugging the implementation. You're inspecting the pull request the agent generates to make sure the plan was sound.
Okay, let's get to the data. This is where the hype gets tested. These benchmarks show whether the model, as you said, collapses once it sees real repositories.
That's right. And we have to look at agent-specific metrics, not just chat performance. The results are pretty telling, especially in areas that need that long-term persistence.
Let's run through them. For real-world bug fixing, the SWE Bench Verified Benchmark, Codex Max solves 77.9% of tasks. That's up from 73.7.
And that 77.9 number is so important. It pushes the reliable bug fixing rate over that 3/4 threshold we've been waiting for. It's a level of reliability that starts to make sense for enterprise use.
But the jump on the SWE Lancer IC SWE benchmark, that one seems to be where compaction really shines.
Oh, absolutely.
That one tests full-stack freelance tasks, a lot of coordination. Codex Max solves 79.9%. That's up from a baseline of 66.3%.
That is a massive jump, 13 points. That's the smoking gun for compaction. SW Lancer tasks are complex integration problems. Older models failed because they just ran out of context trying to coordinate everything. This proves compaction is working where it matters most.
And the last one, Terminal Bench 2.0, long horizon terminal workflows. Here it solves 58.1%, up from 52.8.
It's a smaller jump, but the source notes that in practice it means the agent keeps going longer before it drifts into nonsense.
Yeah.
It's a measure of pure perseverance.
But if you put it all together,
What?
what's the takeaway?
The takeaway is that this is why teams are adopting it. It's seen as the best agent for owning a complete job ticket, not just spitting out a function, but actually closing a complex task on its own.
Owning a job ticket. That immediately brings up safety concerns. If this agent is running shell commands and modifying code, the guardrails have to be perfect.
They have to be ironclad, and safety was clearly a huge focus. On its system card, it has a high refusal rate on malware tasks. A perfect score, actually 1.0, and it shows strong resistance to prompt injection, also a 1.0 score. It basically treats any external text that isn't code with an untrusted hint.
Those perfect scores are reassuring, but what about accidental damage? The source also lists a score of 0.75 on destructive action avoidance. A 25% failure rate there seems risky.
It's a critical point, and we should challenge that. That 0.75 score is from tests where the agent got close to doing things like arm-rf or deleting user data from vague prompts.
So it's not perfect.
It's not perfect, but it's a big improvement. And the mitigation for that risk is layered. It goes beyond just the model's training and into the environment itself.
So the sandboxing, tell us about that.
The environment is built for safety.
Yeah.
If you run it in the cloud, it's in an isolated container. Network access is off by default. You have to explicitly allow it to make outbound calls.
And for local runs?
It uses native OS sandboxing features. And most importantly, its file editing permissions are locked down to only the current workspace. It cannot wander off.
That definitely limits the blast radius. So how does a developer actually start using this thing right now?
3 main ways, all integrated into existing OpenAI services. In the standard Chat GPT Interface Plus Pro Enterprise, you just use the Codex agent mode.
And for those who live in their IDE?
There's the official VS Code extension. You can select GPT 5.1 Codex Max as the backend for an agent session right on top of your local code.
What about for automation, treating it like real infrastructure?
That's the third path, the Codex CLI. That lets you run it headless, which is perfect for CI pipelines, nightly refactoring jobs. That's where it stops being a tool and starts being core infrastructure.
Which brings us to pricing. Max and 24-hour contexts sound expensive.
So it's premium. There's no separate per token price for Codex Max just yet, but the guidance says it'll track with the flagship GPT 5.1 tier. So around, say, 1.25 per million input tokens.
My question is about the xHigh reasoning. If it consumes more limits per unit of work, is that just a hidden cost? How transparent is the price when I kick off a 24-hour job?
That's a valid concern. The sources are clear. xHigh mode does trigger a higher internal multiplier. You are paying more for that guaranteed reliability.
And the transparency.
It comes from pre-job estimation. The system tries to forecast the usage cost based on the scope and the reasoning tier you pick. So you're making a trade-off. You pay more for xHigh, but you reduce the risk that the agent fails halfway and wastes all the tokens you spent getting it there.
That frames it more as a reliability premium. Okay, let's step back. Where does Codex Max fit in the landscape with competitors like Claude and Gemini?
It's pretty clear that Codex Max is leaning into raw agentic depth. Because of compaction and its training, it just outperforms on those long horizon benchmarks like SWE Lancer.
So if you want an agent that can run all night in a sandbox and have a solution in the morning.
Then Codex Max is positioned as the backbone for that job.
And what about the others?
Claude and Gemini are often really strong for natural language analysis, high-level planning, maybe some front-end work where design philosophy matters. The reality is that teams will probably mix models, use Codex Max as the engine for the deep code work, and use others for complementary strengths.
So the big picture here, the sources seem to conclude this is a real move, from autocomplete with better marketing to true autonomous completion.
It is, and that means organizations need to stop thinking of AI as a pair programmer and start designing around agents as core members of the team.
What's the actionable advice then?
Start small. Pick a medium-sized project, give the agent a bounded mission with clear tests, and then measure the results. How many hours of senior engineering time did you save? How often did it land a clean pull request on the first try? That's how you scale it.
So Max is all about context retention through compaction. That delivers reliable long-term agentic work, and the benchmarks back that up.
Exactly. And that 24-hour coding loop is a real capability now. The organizations that win are going to be the ones that treat these systems as core infrastructure. And that raises a really important question for every senior engineer listening.
Which is?
If these agents can reliably own and close those complex, long-running bug tickets, what new, higher-level architectural or design problems are you going to be freed up to finally solve?
That is the perfect question to end on. If you want to dig deeper into the metrics and the compaction engine, definitely check out the original source material. We'll talk to you next time.